Welcome folks, and in today's video we're going to be talking about a very important force called the normal force, which is actually anything but normal. So when students think of the normal force, sometimes they tend to overly simplify it and tend to think of it in terms of just simply opposing gravity. So if we look at L here, and there's a big L stuck to the ground, and there's gravitational force pulling downward on L, then the normal force is opposing that. Now it gets its name from the normal, which means perpendicular to the ground, or perpendicular to the source, the surface that it's in contact with. However, it doesn't always have to be up in an upwards direction, and doesn't always have to simply oppose gravity and be equal to gravity. So we're going to look at that today. So an example of this would be a box sliding down this ramp shown by the letter R here handily, and so the box is going to slide down this direction here, and of course gravity is going to still going to be downwards in that instance, but in this instance the surface is if you draw it perpendicular to the surface, you actually get this third arrow here, which is our force and normal. So our normal force in this case actually is this one here, and so it's not just simply straight up in the air and doesn't oppose gravity. Another example, another easy example that you might have looked at before, is our good sport, our good champ here pushing on the wall, on the end wall, and in this case we're going to have a normal force which is going to oppose that. So it's going to be perpendicular to the wall, so it's going to be this direction. So the normal force in this case is actually to the left, because again it is perpendicular to that wall or contact force. So we can see that weight is synonymous with normal force. And if we use the example shown on screen here, we got a little fish that's doing some training here, and is set up on a weighing scales, and is trying to figure out what their normal force is. Now the weighing scales is going to show a reading of 20 kilograms. Now the weighing scales actually does not show the force of gravity, which is simply the force pulling the fish downwards. Rather, the weighing scales and weighing scales in general show the normal force. So the reading on the weighing scales is taken from the normal force of the fish, which under normal circumstances would be equal but opposite the force of gravity. But what if we add a little bit of weight to this scenario? Then we have a situation where that weight may be able to change. And we're just going to put a bone on the fish. I'm not sure why we chose a bone, but let's just roll with that. Maybe the fish is in weight training, and the mass of the bone is 10 kilograms. Well, now clearly, hopefully through intuition, you'll know that the scales is not going to show 20 kilograms. And if we look at the FG for the fish in question, it would be 192 newtons. Actually, I think that should be 196 newtons. My apologies. But it's not going to simply show 20 kilograms. We know that, we've been on weighing scales before. So we've got to add in a couple of other forces. Now there's an applied force by the bone pushing down on the fish, which is going to be equal to 98 newtons, okay, which is that downward applied force, which is the, if you like, the mg of the bone. And because of that, because this fish isn't going through the ground, because this wonderful thing called normal force, which is actually caused by electrostatic forces, protons, electrons, and so on. We have an Fn here, which is going to oppose these two in the downward direction. So what we can say is that this Fn value here is equal to these two combined. And so when we calculate our Fn value here, we can see that it's the addition of both of those. So it is 294 newtons. So clearly when you push down on something, you are going to get a bigger Fn. Conversely, if we go along to the fish and we give the fish some wings, I don't know why we would give it wings, and we get rid of the bone, we'll see that there will be a buoyant upwards force, and that would allow, if we're getting rid of this bone here, that would allow a lift up on the fish. And if you provide a lifting force, you're actually going to get the opposite. You're going to get a less Fn value. The scales will show, the scales reading are going to show a lower value. And that's because there is an applied force upwards. And again, those need to be balanced. So the weight is not always the weight, I guess, is the key point here. How do we expand this on? So we can actually just play around with this a little bit. So it's clear that weight isn't always weight. There is certain instances where there is an apparent weight, and this is where there's a pushing motion downward on an object that's on a weighing scale. So we're pushing down, or indeed with the wings if we're releasing some of that normal force. And the apparent weight is that sort of feeling. It's a sensation. It's that feeling of weight, the feeling of weight change. And that can change depending on whether something is pushing down or up. And there's another example that I want to show you, which is where the Fn can be increased or decreased by acceleration up or down. And so if we use this as an example here, we've got a situation here where we've got a plucky volunteer, and this volunteer is going to help us out for this, and said volunteer can go up or down in the elevator. Now at the beginning, obviously if we look over here, we can see that the FBD for that situation at rest is very simple. Fn is opposed to Fg. Now, if we take the person starts accelerating upwards in the elevator and we take a snapshot at this point here. So they've been moving, they're now starting to accelerate upwards as an elevator does. We'll see a number of things. So firstly, we'll see that they're moving with a velocity upwards. And their acceleration is also upwards. Now in this case, that means there's an unbalanced force in the upwards direction. So we need to account for that. The person will still have Fg here. The force of gravity is still going to be acting on the person, but they're accelerating upwards, which means that they're not balanced. So in that instance, this Fn is going to be much bigger, this Fn value. Okay, and there's an unbalanced force, and that unbalanced force we call F net. And we're going to look at some problems later on for that. A common mistake students make is they start thinking about this in terms of Ft. The person is in the elevator, so it's the ground that's actually pushing up on the person. There's no cables, anything like that. That's external to the elevator. It's a different system. So if we continue our travel up the elevator, at this point here, person has accelerated and now they want to reach the destination, and as they're reaching the destination they start to slow down. And if they start to slow down, of course we still have the velocity is moving upwards, but now we have our acceleration value here is downwards because they're slowing down, so the acceleration and velocity are in opposite directions. So we still have Fg downwards, but now what we've got is we've got an Fn that is smaller because the overall net force is down. So the sensation of the person in the elevator up here at this point here is they would feel lighter. And if we go back to our scenario earlier, if we just go back to this scenario earlier, they will feel at the midpoint when they're accelerating, they will feel heavier. Okay, so now we can go across and we can look at an example of where they're on their way down. Start from rest. Now they start accelerating. Again, the acceleration here, if they're accelerating downwards, what that means is that there's going to be less of a force upward acting on the person. So the acceleration is going to be downward. And so if we mark that in here, we've got Fg and we've got Fn, which is going to be less because Fnet is pointing downwards overall because the acceleration is downward. And what that means is because of that lower Fn value, this person here is going to feel a wee bit lighter. And you've probably experienced that in elevators where you felt that you felt a little bit lighter as the elevator was moving downwards. And that's that effect, just feeling a little bit lighter. So quickly, just some normal force problems or apparent weight problems. Consider a monkey standing on a scale. Why does monkey stand on a scale? Who knows? Who cares? But they are, and they're loving it. The monkey is holding a helium balloon, which of course I've colored in a heart shape, had to be. The balloon pulls upwards with a force of 50 newtons. What is the reading on the scale now? So this is an example of where there is an upward force. And that upward force is going to mean that Fn, the normal force, does not just simply equal and cancel out Fg. So if we look at our FBD, just before we look at our FBD actually, we should probably always consider doing a sign convention so we know which side is positive, is it up or down, and we stick to that. We can also see there's the force of gravity acting on the monkey, which is simply 9.8 multiplied by 100. And we also see this balloon force or buoyant force or whatever, which I've called FB, which is 50 newtons. So if we are to have a look at this, we can see that overall the Fnet value is going to be 0. So this Fnet value over here is going to be 0 because the monkey's not accelerating up or down. And so if we rearrange our terms here, we get that Fn is equal to negative Fg minus Fb. Now, of course, if we're sticking to our sign convention, then the downward force had a negative, which makes this whole thing positive. So we have 980 minus 50 newtons. And so it turns out that in order for these forces to balance, we have to have an Fn value of 930. So we can see that now, again, you can see that the Fn value is not equal to an opposite to the Fg value because of this slight upwards force, which is causing the monkey to feel a little bit lighter. Second type of situation where the Fn can change we talked about is something like an elevator. So an example in front of you here, a person of mass 80 kilograms is in an elevator at the CN tower, having the time of their life going up and down the elevator. Find the Fn value when the person is at rest or accelerating upwards. So the person's in here in an elevator in the CN tower. When they're at rest, of course, we should know, or I should say at rest or moving with a constant velocity. In other words, no net force. Then only in that case can we say that Fn is equal to mg, or the negative of Fg rather. And so in this case, it's just simply equal to 784. And the reason for that is because this Fnet y, which is the combination of forces, is equal to 0 because there's no acceleration. And that would be if the person's at rest or moving with a constant velocity. So we've got this one done here. What about B? B is accelerating upwards at 4 meters per second squared. So now we do actually have an acceleration and that acceleration we're told is 4 meters per second squared. And so that's useful because we know that the Fnet value, the Fnet y value, is now not equal to 0. It's equal to the mass times acceleration, which is equal to 80 multiplied by this acceleration value, which is 4. And so that's equal to 320. And this is useful because we know there's an unbalanced force upwards, and we know indeed that that's caused by the force, the normal force, as we described earlier. So we know that the normal force is 320 320 newtons bigger than our FG. Now in this case, I'm going to stick to what I did in part A, and I'm going to say that upwards is negative in this case. As long as we say downwards is positive, we're okay. And so the acceleration should have a negative, and this should be a negative, because we've set this as a positive. So very, very important that you do that. And you can work this out using equations, but basically it is going to be 320 bigger than that. So it's going to be 1104, I believe. Okay, so that's an example of where you have two examples where normal force is not the normal force, is not so normal, not equal to force of gravity. Hopefully you found this to be a little bit useful. And if you did, please just give me a like and subscribe to my channel.